All right, a very good evening, everyone. So, we are into the fifth lecture of social media analytics, and today we will be discussing the following topics. So previously we have in the last lecture we have left few of the algorithms that are important for calculating the network measures. So these were the traversal algorithms, the breadth first search, the depth first search. Then we have the shortest path algorithms, that is Dijkstra algorithm. So we will be quickly seeing one of the example and quickly going through its algorithm. Then we will also see that how do we calculate minimum spanning trees. Then like next we will move on to the network measures. That is one of the network measure that we are going to discuss in today's lecture is the clustering coefficient. After discussing the mathematical part and the algorithm of clustering coefficient, we will move on to calculating the centrality. So centrality calculation is one of the very crucial calculation or one of the crucial operation in social media networks. So by calculating the centrality, you want to identify that which of the nodes are more important. You want to rank the nodes. So there are different ways in which centrality can be calculated. So we will be seeing three ways in today's lecture. So that includes degree, closeness, and betweenness. So we will be covering the examples of all these three betweenness, closeness, and degree centrality measures. So after doing that, like we might, if like time permits, then we might cover eigencentrality as well. So eigencentrality, it works as the base for PageRank algorithm, or the algorithm that I have discussed many times, like I have mentioned many times till now, that this particular algorithm is used by the Google. So yeah, so with that, let's start with the algorithms. So I hope like my screen and everything is visible. I'm audible and my screen is visible to you.
Yes, ma'am. Ma'am, one thing, the last lecture's PPT is not uploaded. So,
Yeah, yes, yes. So I will upload it today, both the PPTs, today's and the previous lectures. I'll upload it. So I missed uploading the PPT, last PPT. I'll upload it today.
yeah, and is it possible to upload the next coming lectures PPT as well?
Coming lecture PPTs, I can only upload on maybe the Fridays or Saturday, like Saturday morning. So before that, it will not be possible. So maybe Fridays, I'll try to upload the PPT.
Okay, ma'am. Yeah, that would
Yeah.
be helpful.
Okay, okay, sure. I'll try to upload the PPT previously. Either like I can upload on Friday or maybe like Saturday morning I can upload it.
Yeah,
Yeah.
sure.
Okay, so let's start with our tree traversal algorithms. Okay, so what all are the traversal algorithms? Basically, like we have two traversal techniques, that is the depth first search and the breadth first search. Okay, so these two techniques, they form the basics of most of the algorithm when we are trying to identify the shortest paths, when we are trying to do other advanced algorithms. So these two techniques forms the basis of identifying those like complex algorithms. Okay, so we will quickly go through an example and we will quickly see first why calculating breadth first search and why covering these two is important. So traversal algorithm, there are two traversal algorithms, that is breadth first search and the depth first search, and there are various different variants of variant implementations of these two algorithms. And these two algorithms are very important in social media analytics. Okay, so because you need know that like in social media, the data that we have is in the graph form. We have the nodes and edges and communities. So these form the very important algorithms. Okay, so why they are important? Firstly, when for like various community detection algorithms. So whenever we will be studying these community detection algorithms, So there also BFS and DFS, they forms the fundamental algorithm for identifying the clusters and for identifying the friends of friends. Okay, so whenever you want to identify the ego networks, so what all are the ego networks? Ego network is when you want to find the connection of a person's friends of friends. Okay, you want to identify that what is this person, who all are the friends to these people, person, and further, like at next level, who all are the friends of friends. So this kind of network is called as the ego network, and BFS plays a very crucial role when we want to identify these particular ego networks. Okay, so first application of the traversal algorithms is identifying the communities or the group of people that are closely connected. Then the next application of traversal algorithm is the information diffusion. Okay, so you want to identify that how a particular information, if we select a particular person in the network, or in the other words, in the technical terms, we can say that if we select a few seeds in the network. Okay, by seeds I mean that few selected people. So how the information spreads. Okay, so we will be seeing that okay, this is the person, the information will spread from this person to all its neighbor, then all the neighbors will further spread the information to all the other neighbors, and so on. So here BFS plays a very crucial role. Okay, then also like you see that in Facebook we have the various algorithms which suggest you the friends. Okay, so you get these friend suggestions that you can add these people and so on. Then you may get the suggestions like these are the pages that you might like. So these recommendation pages are also identified by using these kind of algorithms. So you see that BFS and DFS, although they are very fundamental algorithms that we study in the graph algorithms, but they form very fundamental, and they are very fundamental, and they are very crucial when we are trying to do these complex tasks. Okay. So firstly, we will see what is depth first search. So in depth first search, we start with a node. Okay, we start with a node, select one of its neighbor from the neighbors of node vi. Okay, so first what we will do, we will select one of the node, we will start from that node, and then we will select one of its neighbor. Okay, and perform the depth first search on that node, and then again we will try to find one of the neighbor of that particular node, the selected node, and so on. Okay, so in order to implement DFS algorithms, we require stack structures. So if you have covered the algorithms, can anyone tell me what are the stacks in algorithms?
First in, first out. Oh, sorry, last in, first out data
Right.
structure.
Right, right. So we will be using a last in first out data structure in order to implement the depth first search algorithm. Okay, so let us try to understand with the help of this example. Okay, so suppose we have this particular graph. Okay, so we will start with a node. So we will start with node vi. So in the exams, you might be asked that give a sequence of nodes by like give a sequence of nodes in which you are traversing the nodes, and you have to use DFS algorithm. So what will be the answer? Or by using BFS algorithm, what will be the answer? And you might have to show the steps. Okay, so basically understanding the intuition behind these two algorithm is very important. So these days like through the generative AI, and like as in Python we have lots of libraries, so it's not like it's very easy to implement these algorithms. So you simply have to use the functions from the library, but basically getting the intuition behind these algorithms is important. So that is what like I would prefer to ask in the exams. Okay, so in depth first search, how you solve this problem, you will start with a node. Okay, so then you will push this node in the stack. Okay, and then you will push all its neighbors also. You will push all its neighbors. So then you will pop out the first neighbor. So you will pop out the first neighbor, maybe that is V2. Okay. So you will pop out this neighbor, and then for this particular node, again its neighbors, you'll push it in the stack. Okay. Now you have pushed V5 and V4 in the stack. So now what you will do is, since the last node added can be taken out, so you will take out V4. Okay. So you can see that here we are traversing the whole graph in depth first fashion. Okay. So you are taking a node, you are taking its neighbor, then you are considering that node as a parent node, you are taking its child. Okay, and so on. Once you reach V4, you will check that whether it has any children. So this particular node does not have any children. Okay, so now you will pop out this particular node from the stack. Okay, and you will then again pop out the next neighbor of V2, that will be V5. Okay, so now again for V5 we will check whether it has any children or not. So the answer is no. So because like it does not have children, so this will get pop out. Then again, because we have traversed all the children of V2, V2 will also get popped out, and so on. Okay, so this is the way this algorithm is implemented. So whereas if we have if we have the same algorithm, okay, and we want to implement it by using breadth first search, so how it will be traversed? So anyone can give me the series of the nodes that if we use breadth first search on the same tree, so what will be the answer of the traversal? How it will be traversed?
Oh, it will be V1, V2, V3, V4, V5, V6, V7.
Correct, correct. So this will be the order if we are doing the breadth first search. So in order to implement the breadth first search, we use queue. So can anyone answer what are queues?
First in, first out.
Correct,
So
correct. So we will be using queues to implement breadth first search. So in that, initially, you will start with traversing V1. I'll go to the next example. So since you have already covered these algorithms, breadth first search and depth first search, that's why I'm not going into much detail of these two algorithms. So yeah, so let's go through the example. So we will start with V1. We will traverse all the neighbors of V1. So the neighbors of V1 are V2 and V3. Okay, so now starting from V2, we will traverse all the neighbors of V2, then all the neighbors of V3, and so on. So this is how we do breadth first search, and I've already told you that how we do the depth first search. Okay, so now next we will move on to identifying the shortest path. So this is again a very important, one of the another important algorithm. So this algorithm again, it sometimes use these BFS and DFS, depth first search, to implement it. Okay, so now we will see what is Dijkstra algorithm and how Dijkstra algorithm works, and how so it is a shortest path algorithm. So starting from a node, it identifies shortest path to all the other nodes that are present in the network. Okay, so we will start with the source node, and from that node this algorithm help us to identify the shortest path to all the other nodes that are present in the network. Okay, so now in the networks, you might have this problem where you need to identify all pair shortest path. So when you need to identify all pair shortest path, what you can do, either you can apply Dijkstra algorithm on all the nodes. Okay, so when you will apply Dijkstra algorithm on all the nodes, for each node, you will identify its shortest distance to all the other nodes. Okay, or there is another algorithm, that is Warshall algorithm. So you can apply the Warshall algorithm to find all pair shortest paths. So now let's read what is there in this slide. So when a graph is connected, there's a chance that multiple paths exist between any pair of nodes. In many scenarios, we want the shortest path between the nodes. Okay, so this is the requirement. Maybe when we are calculating the communities or when we are calculating the centralities. So we need to calculate the shortest paths. Okay, so when I will be explaining you the betweenness centrality and the closeness centrality, you will know that okay, this is one of the operation that need to be implemented in order to calculate the centralities in the network. Okay, so we need to have a fast method. We need to know that what algorithm to use in order to identify the shortest path from one node to all the other node. So Dijkstra algorithm is designed for weighted graphs and for non-negative edges. Sorry, with no non-negative edges. So Dijkstra algorithm is the algorithm that fails whenever we have negative cycles in the graph, and it may or may not fail whenever we have a negative edge. So generally, the Dijkstra algorithm, it works only for positive edges, I can say. Okay, so it finds the shortest path that starts from a provided node to all the other nodes. So we have already discussed this, that Dijkstra algorithm, it identifies the shortest path from one node to all the other node. It finds both the shortest path as well as their lengths. Okay, so in order to implement the Dijkstra algorithm, so this is very important. Let's see like what will be the initialization. So after covering the initialization, I will give you one example, and then like we will again discuss these steps to and fro to understand that how this particular algorithm works. Okay, so first, how we will initialize our network? We will assign 0 to the source network. So source network is the one from where you want to identify shortest path to all the other nodes. Okay, so you will initialize that source node with 0. Okay, so this is very important whenever you are starting this algorithm. Whatever is your source node, you will initialize it with 0, and you will initialize infinity to all the other nodes. Okay, and what you will do, you will mark all the nodes as unvisited. So since like we are starting this algorithm, so in the starting all the nodes will be unvisited, and set the source node as the current node, and we will set the source node as current node. Okay, so now I will give you one example. Okay, so let me take this graph. Okay, so maybe I have A, then B, then C, then I have D, E, F. Okay, so I would suggest that all of you should note down this particular example and solve this example along with me. So the Dijkstra algorithm, it works for both directed edges as well as undirected edges. Okay, so this is the initial network that I have, and now I will initialize the weights on the edges. Okay. So this is our initial graph. Okay. I hope everyone has noted down this algorithm. Should I wait for some time?
So, ma'am, we can proceed. I mean, I have noted.
Okay. Okay. Okay, so what will be the output of Dijkstra algorithm? The output will be sequence of vertices that are identified by Dijkstra algorithm. So this sequence of vertices gives the shortest path, as well as using this Dijkstra algorithm, we will be finding what is the length of the shortest path from a source node to all the other nodes. Okay, so now in this particular algorithm, first of all, we will be initializing. Okay, so we have these nodes A, B, C, D, E, and F. Okay, so let us take A as a source node. Okay, so since A is the source node, it will be initialized by 0, as I have explained in the initialization, and rest of the node will be initialized by infinity. Okay, and all these nodes will be marked as non-visited. Okay, so now initially what we will do is we will start with node A. Okay, so A is our source node from where we are going to start. So A is the source node, and from source node A, we are going to identify which are the nodes that can be reached. And for those nodes, we are going to calculate the cost function. Okay, so now let us see what is cost function. Okay, so see, initially we have initialized all the nodes as the distance to all the other nodes as infinity. Okay, so now whenever we start, we identify all the nodes that can be visited from the starting node. Okay, so once you identify all the nodes that can be visited from the starting node, we will calculate the cost. The cost will be the cost will be the distance from that starting node to the nodes that to the neighboring nodes. Okay, so that will be nothing but the weight of those edges. So now yeah, so in each step what we will be doing is from each source, from each node, suppose here we have A. Okay, so now from A I will see that what all are the nodes that can be reached from A, and I will see that what all is the distance. Okay, so for example, B is 6, so B can be reached in with the distance 6. Okay, and 6 is less than infinity here. Okay, so we will update this distance here. So this is 6, and it is reach we can reach B from A, so we will update that from where we are reaching. Okay, so next we will see that which all are the other nodes that can be visited. So now C can be reached, and we will update the cost, that is, or the distance, that is 90. Okay, then what all are the other nodes that can be reached? E can be reached, right? So E can be reached, and the cost is 70. Okay, so now this is the cost function at second step. Okay, so now after visiting A, so now we will see that which is the minimum cost or which is the minimum distance amongst all the other nodes. Okay, so we can see that the cost function of B is minimum. Okay, since cost function of B is minimum, so B will be selected to be visited next. Okay, so yeah, so this is the path that have been selected. So now we have selected B. Okay, so now from B, again we will calculate that which all node we can reach from B, and the cost function will be the cost till B plus the cost from B to the next node. Okay, so if that cost is less than the cost that is already there in the database, okay, so if that cost is less, then we will update that value. Okay, so now this point will be more clear if I see. Okay, from B we can reach D, right? And the cost is 47 here. The distance is 47. So the total distance will be 6 plus 41. Sorry, 6 plus 41, that will be 47. So the here we will update infinity and infinity. Now in the next step, we have uh, till D is 47 and we are trying to reach from B. Okay. Then what all are the other nodes that can be reached from B? I think there is no other node. Okay. So now these are the current costs we have. 70 from A, 90 from A, and 47 from B. I hope this calculation of 47 is clear to everyone.
Can you repeat that, madam, please?
Okay.
47.
Okay, so 47 is what was the cost to reach till B? The cost to reach till B was 6. Okay, so now from 6 we are calculating that what all other nodes can be visited and what is the cost. Okay, so now we can see that we can reach D. Okay, and the cost to reach D is 47. So the total cost will be for 6 plus 41, that is 47. Okay, so the cost to reach D will be 47. So now is it clear to everyone?
Yes. Yes.
Okay, so now at this step again we will see that which particular node has the shortest distance. Okay, so we can see that this path from B, okay, so this path from B has the lowest cost, that is 47. Okay, so now we will select D to be visited. So at this step we are selecting D. So that means we have selected this path. Okay, so now again from and now we are at the point D. So from D till in order to reach D, what was the cost? The cost was 47. Okay, so now we will try to see that what all are the other nodes that can be visited from D and what is the cost after reaching those points. So now if we want to, we can see that there are the outgoing edges. There's only this outgoing edge and this is to C. Okay, in order to reach C, now I have to add the cost 47 plus 12. Okay, so is it clear or is there any doubt, anyone? So we have selected D to be traversed. Now from D we are calculating. So from D there's only one outgoing edge and that is to C. So now we will see that what is the cost to reach the C. So the cost will be 47 plus 12, that will be 59. So we will see that what was the previous length of the path in order to reach in order to reach C. So previous was 90. And now like after going through this path, what is the current cost? The current cost is 59. So what we will do is we will update this value. So we will update it, that is 59, and we are trying to reach from D. Okay. And is there any other updation we can do? So see, there is another outgoing edge here, that is to A, but A is already traversed. Okay, so from A we have A is already visited once. So A we will not calculate this distance to A again. Okay, so yeah, so other than that there are no edges. Okay, so now what all are the current costs we have? We have 59 from D and we have 70 from A and then infinity not visited. Okay, so now amongst these which is the minimum cost, which is the node with minimum cost?
C.
C. So right. So now we will choose C to be visited. Okay. So now we have chosen C to be visited. And the cost to reach till C is 59. Right. Now we will check from C. From C, where can we go? The first outgoing edge is to B. But B has already been visited, so we will not touch B again. What all are the other outgoing edge? There's one outgoing edge to E.
E.
Right. So we will calculate the cost. What is the cost if we are going through C? So the cost is 59. 59 was the previous cost. 59 plus 10. Okay. So that comes to 69. So since 69 is less than what we already had, so we will update this value. So this is 69. 69, and we are trying to visit from C. Okay, so is there any other outgoing edge? So the answer is no. Okay, so now at this point we have only this option. Okay, so what we will do is from C we will visit E. Okay, so now cost to reach till E is 69. Okay, so now in the next step we will see that from E where all we can go. So we can go to D, but D has already been visited. So again, we are not going to touch that. So then there is another outgoing edge here, that is F. Okay, so now we will calculate the cost. The cost will be 69 plus 15. 69 plus 15, that is 84. Okay, so 84 is less than infinity. So we have here 84, and we are visiting from E. Okay, and now at this step we have only this option, so next F will be visited. Okay, so this is the shortest path from A to all the other nodes that is being calculated by Dijkstra algorithm. So I hope this entire calculation and the way in which Dijkstra works is clear to you. Is there any doubt, anyone?
Ma'am, calculation is clear, but what is the negative edge? Because this we mentioned that this algorithm works only for non-negative.
Yes, yes. So see, so now suppose there was this negative edge. Okay, so let me take this example. Suppose I had this negative edge. So in this case, क्या होता कि like when you are at D and you like see this calculation. So now you will see that the cost is less. Okay, so the cost has reduced than what it was before. So this because of these negative edges, the algorithm fails. So that's why this algorithm does not work for the negative edges. And especially like if you have the negative cycles, the cost will keep on decreasing. Okay, so you are visiting the nodes, and like the more you reach, I hope like you understand what is a negative cycle. So if you are going through a negative cycle, the cost to reach the nodes will continuous decrease. So if it is continuously decreasing and there is no minimum thing that we are getting, okay, so in that case, obviously the Dijkstra algorithm will fail. So I hope the question is clear.
So from this example context, yes, it is clear. But if we need to present an example about a negative edge and non-negative edge, how we can present it?
Okay, so maybe then like currently I do not have an example. So maybe we can search for an example and we can see that how this algorithm fails. So maybe like maybe I can give you the question in next class, where like you can yourself calculate and see that how it is failing. So currently I do not have the example with me. So yeah. And also I remember there was one question in the last lecture as well. So there was this question someone asked me that whenever we have strongly connected components, So can those be overlapping or not? So someone asked me this question. Do you remember that? So anyone has answer to that question? So whenever we have strongly connected components, so can those components be overlapping or not?
I asked, but I don't have answer.
Okay, okay. So yeah, so the answer is that the strongly connected components cannot be overlapping. Okay, so the strongly connected components cannot be overlapping. Why? Like these strongly connected components are always minimal. So if so, you know what is the definition of strongly connected component? If you reach one node, you should be able to reach all the other nodes. Okay, so from a strongly connected component is the subgraph in the directed graph where you can reach from one node to all the other node. Like there is a two-way path. You can reach from A to B and you can reach from B to A. Okay, so there is a path in every pair of nodes. Okay, so now if you have another node, another overlapping node from another component that can reach one of the node. So if it can reach one of the node, it should be able to reach all the other nodes. So that's why these strongly connected components are disconnected. These are disjoint. These are not like overlapping. So अगर overlapping होंगे तो एक को अगर वो visit कर सकता तो सबको ही visit कर सकता ना तो this entire will become a strongly connected component. So that's why like last time I didn't have a proper answer to this. Even I was not sure. So yeah, so this is the answer.
Got it.
So yeah, so after this, let's quickly go through these steps. So now, like when we will go through these steps, it will be more clear to you and it will be more intuitive. So the current node, for the current node, consider all of the other nodes as unvisited neighbors and calculate the tentative distance. If tentative distance is smaller than neighbor's distance, then the neighbor distance is equal to the tentative distance. So we were calculating the new tentative distances. So if the new tentative distance was smaller, then we updated those values. After considering all the neighbors of the current node, mark the current node as visited and remove it from the unvisited set. If the destination node has not been marked visited, or if the smallest tentative distance among the nodes is unvisited, set it infinity and then stop. Set the unvisited node marked with the smaller. Yeah, you can read these steps and it should be like pretty intuitive. If you understand this particular example, you should be able to understand the algorithm that is there behind this. So Dijkstra is the algorithm that finds the shortest path from the source to all the other nodes. So we have already seen that. So we can run, if we want to find the shortest distance between all the pair of nodes, so we can apply this Dijkstra algorithm to all the nodes. So currently, like in the last example, we have applied it to node A. So if we apply to node A, I can identify the shortest distance from A to all the other nodes. Now, suppose I want to find from B as well, from C as well, from D as well. So I can apply this algorithm to all the nodes in the graph. Otherwise, we could have used there's another algorithm that's Floyd-Warshall algorithm. So otherwise, we could even use this algorithm. So I think this particular algorithm do not fail for negative edges. It works for negative edges. So still, but I will confirm it and I'll tell you in the next lecture. So yeah, this particular algorithm, it do not fail for negative edges. If we want to compute the shortest path from a node V to the destination, okay, so yeah, it helps us in identifying the shortest paths. So this is another example that is given in the slide. So when I'll upload these slides, you can work out this example as well. So that like the entire Dijkstra algorithm, how it runs, the different steps are clear to you. Okay. So next, we see the algorithms to identify minimum spanning trees in graphs. Okay, so what is a minimum spanning tree? So the minimum spanning tree is a subgraph in the graph. Okay, so it is subgraph. What is the subgraph? Subgraph is a part of the graph that connects all the nodes and that has no cycles. So basically in this, we will have all the nodes, we will have no cycles, and we will choose the edges such that all these nodes are connected. Okay, and all the remaining nodes, all the remaining edges are removed, and the total edge weight is as small as possible. Okay, so minimum spanning tree is such that like all the sum of all the edges should be minimum, there should be no cycle, and it should have all the nodes that are connected. Okay, so the minimum spanning tree will have all the nodes. So if your graph has n nodes, then it will have all the n nodes. Okay, then it has exactly n minus 1 edges. So since we do not want any cycles to be there, and since we want the minimum spanning tree to have minimum weight, so that's why there will be n minus 1 edges in the graph, and the weight will be minimized, and there will be no cycles. So now there are these two popular algorithms to identify the spanning trees. So the first one is the Kruskal algorithm, and the second one is the Prim's algorithm. So what is the intuition behind these two algorithms? So in Kruskal algorithm, what we do is we have these edges, we have this graph, and we have the edges. Okay, so now one by one we sort the edges by weight, and we add the smallest edges in the spanning tree, in the minimum spanning tree, and we skip if the cycle is there. Okay, so this is how the Kruskal algorithm works. So let me explain you with the help of an example. Okay, so suppose I have this graph. Okay, so sorry, I am not sharing my screen, tab screen. Okay, so this is the example. So if you want, you can note down this particular example. So have you noted down? Should I solve this question?
Yes, ma'am.
Okay, so yeah, so in the Kruskal algorithm, we sort all the edges, and then one by one we pick the edges with the like starting from the minimum weight, and if there's any cycle, then we will not add that edge in the spanning tree. So in this particular case, which is the smallest edge, which is the edge with the smallest weight?
AB 10.
Correct.
A,
So firstly, in the spanning tree, this particular edge will be added. Okay. So now next, which is the next smallest edge in the network?
ED.
Correct. So next ed will be added. So when we add each edge, we check whether like there's a cycle or not. So if there's no cycle, it's fine, like we can add this edge in the spanning tree. So next again, we will try to identify which is the third smallest edge in the graph.
AE.
AE. Next, which is the next smallest edge?
AD.
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 AD, AD. Okay. So yeah. So now if I add AD, okay. So if I add AD, there will be this cycle. But spanning tree does not have cycles. So we will skip AD. We will not put AD in the spanning tree. So after that, we will see that which is the next smallest edge. So next smallest edge is BC or CD. Okay, so we can add either of these two edge. So maybe I add this edge. So this becomes the spanning tree.
Ma'am, EB is there, right? Next. E to B.
E to
B.
Yeah, that is also cycle.
That is also cycle.
yeah, right. E to B, that is also cycle, right? So yeah, so because it is forming a cycle, we will not add this edge. So this becomes the spanning tree. Spanning tree is a subgraph that visits all the nodes and it has minimum edge weight of the entire cycle. And like there are only, if there are n a number of nodes, there will be n minus 1 edges. So this becomes the spanning tree using the Kruskal algorithm. So, yeah, so in this particular example, you can also see that there are more than one minimum spanning trees possible by using this algorithm. But this is only possible whenever we have repeating edge weights. So in this particular case, we could have like chosen not to add CD edge in the spanning tree, but BC edge. Okay, so there can be more than one spanning trees in the network, and like this happens only when we have repeated edge weights. Okay, so now let us see that how Prim's algorithm works. So there's another algorithm called as Prim's algorithm to identify the spanning tree. In this, we start from a node and repeatedly add smallest edges that connect to the new node. So Prim's algorithm is very similar to how Dijkstra algorithm works. Okay, so in this, for example, like let me take another example here. So okay, so suppose I have this network. Okay, suppose I have this network and these are the edge weights 15, 10, 20, 12, 2, 1, 4, 5, and 3. Okay, so now in this particular algorithm, we start from a particular node as we have done in the case of Dijkstra algorithm. Okay, so first everyone note this particular example.
Ma'am, may I ask a doubt in Kruskal algorithm?
Yes.
Uh, no, No, if you can go to that screen ma'am, where you had shown the example.
Yes.
Like now, if we have a situation like if there is a node from B and it is going to say E with a weight of say anything like 50,
Okay.
and it is not connected to any uh, other node, only connected to B, then how this spanning tree will provide the complete span?
Okay. Just a second. So you are saying that here, if we had weight 50,
No, no, ma'am. B to C is okay, 40. But if there is another node E, which is going from B with a weight of 50,
okay, so
and is
maybe
not
F.
connected to,
Okay.
Hanji,
So
ma'am,
you
you
are saying,
can take
and then we have here another
a
edge
weight of
that
50.
has 50. Okay.
Yes,
So in this case, see, हमारा requirement क्या है? Requirement is कि सब nodes को visit करना. Okay.
yes,
So we
ma'am.
have to, your spanning tree should have all the nodes, and it
Yes,
should
ma'am.
have like a minimum number of edges that connect those nodes. Okay. So if there is only one edge that is going to this particular node, then we need to add this edge as well to the spanning tree. So then in this particular case, this will be our spanning tree. So we have to
Okay,
keep
ma'am.
on executing this algorithm until all the nodes are visited.
Okay, okay.
So yeah, we are at Kruskal's algorithm, sorry, Prim's algorithm. So in Prim's algorithm, we will start with node A. Sorry. Let me again work through this example as we have done the Dijkstra algorithm. So we have these nodes A, B, C, D, E. Okay, so now A is the source and it is not visited. Rest we will initialize by infinity. And again, these are not visited, not visited, not visited. Okay, so now from A, I will see that like where all we can go. So we can go to B. If we go to B, then we have 15. And here we will update that we are going from A. Okay, so here we selected A. A is visited. So then it can go to D. Okay, and the cost to go till D is 10. Then we can go to E as well. The cost to go to E is 20. Then we can go to C as well. So the cost to go to C is 12. Okay. So now in this case, again, we will see that like which is the minimum cost. Okay. So the minimum cost here is from A, from to C. So we add this particular edge here.
Ma'am, to D.
D.
D is
One sec.
10.
Okay. Sorry. Sorry. Yeah. Right. Okay. So now here D is visited. Now from D, we will try to see that what all are the edges that can be visited and what is the cost of those edges. Okay. So now from D, we can visit B and the cost of the edge is 5. Okay, so in the earlier case, in the Dijkstra case, we were building the cost on the previous cost. Okay, so we calculated that what is the cost to reach to D, and then using that particular sum, and then we added this another weight to reach to that, to the neighbors, to the next neighbors. But here there is a slight difference. What we will do is we will see from D which all nodes I can visit. I can visit B. So what is the cost to visit B is 5. So simply if 5 is less than the previous edge cost, so I will update it. So we have 5 here, and 5 can be reached from D. Then we have C. C is 1, 1 can be reached from D. Then we have E, and the cost is 3, and it can be reached from D. Okay, so now in this case, again, we will see that which is the minimum edge weight. So the minimum edge weight is this one. Okay, so now in the spanning tree, this particular edge is added. That is DC, DC, this one. Okay, so now again, from this C, we will see that where all I can visit and what is the cost of those edges. So first we will see we can visit B, right? And the cost of B is, I have not written. Okay, so let us suppose the cost of B to reach B is 2 here. Okay, so now if I want to visit B from C, the cost is 2. So 2 is less than 5, so I'll update here. So 2 from C, here C was selected. And then I can also reach E. And in order to reach E, what is the cost of the edge? The cost of the edge is 2. So again, that is less than what we already have. So we will update it. Okay, so now in this step, we will see that which is the minimum cost of edge. So the minimum cost here, like we have the same cost to both these edges. So we can choose any. So maybe I chose this, and we add this particular edge to the spanning tree. Okay, so now again, next it will see that what is the minimum cost to reach to C. So that was to E. So that was from C, and this particular edge will be added. So this is the spanning tree that is built by Prim's algorithm, and this is the Prim's algorithm. Is it clear to everyone? Any doubt in this algorithm? We'll start from a node, repeatedly add the smallest edges that connect to a new node.
I mean, can you explain the last step from
Okay, so
D
here
from B to E? How we have reached? It should be 4, right?
from B to
E.
from B to E. Okay, so now from B, we will try to see. Okay, so from B, if we add this edge, what is the cost of the edge? The cost is 4. Okay, but
4.
we already had a minimum cost. Minimum cost was 2 from C. So since this 2 is less than 4, so we will not update that cost. We will keep it like that only. And then in next step, we will see, like after selecting B, we will now see that which is the node that has to be visited, and so like this particular data will be used. So that's why this edge is added, C to E.
Thank you, ma'am.
Yeah. So like, can you identify what all are the differences between Kruskal algorithm and Prim's algorithm?
One is the
Any?
weight calculation. We are calculating weights from the start of the node.
So yeah, so in Prim's algorithm, we already always have a connected spanning tree. Whereas in Kruskal algorithm, you have seen that in between we got a disconnected spanning tree. So when we added this first edge from A to B, next we added E to D. So this was a disconnected network. Whereas when the calculation in the Prim's algorithm, it always gives a like from one step to another, we always have a connected tree, the connected output. And then Prim's algorithm, it is more useful when we have dense networks, whereas Kruskal works better when we have sparse networks. Yeah. So, okay. So here we will take a short break, and then like after coming back. Okay, so this is another example. I have given you another example in the explanation on the iPad. So when you get these slides, practice this particular example. Okay.
Ma'am, both the algorithm can be work for directed or non-directed graph?
Yes, I think. Yeah. Let me check.
Okay,
I'll check and give you the answer.
okay.
Yeah. Okay. So with that, let's take a quick break. We will be back in 10
Ma'am,
minutes.
one last question. Ma'am, that quiz and um, assignment states, can you publish it, ma'am?
Okay. Okay. I'll
Oh,
publish. Yeah. Yeah. I'll
thank
do
you.
that. Yeah.
Thank you.
Okay. Hello, everyone. Welcome back. So, up till now, we have discussed the basic fundamental algorithm of graphs. Okay, so these were the algorithms that you already must have seen in your data structures or while studying the algorithm, while studying the graphs in maths. So these were those algorithms that we have discussed till now. So, from now onwards, I will be discussing certain measures that tell you certain properties about the social media network. Okay, so these will be some of the properties that are very important when you are trying to analyze these social media networks. Sorry, I haven't shared my screen, right? Okay, yeah. So, if you see on this slide, so now we will be discussing what is transitivity in the network. So if you see in this slide, suppose Rishabh and Shubharo, these both are friends, okay? And Shubharo and Vibhas, these both are friends. So now if these both, you have this mutual friend, that is Shubharo, then probability of Rishabh and Vibhas becoming a friend increases. Okay, so let me take a real world example. So suppose like we have a Rajat and we have Gaurav. So these people, although they don't know each other, but then they have lot of people, lot of friends, lot of common friends. Okay, so these both have lot of common friends. So if two people have lot of common friends, then probability of their becoming friends increases. Okay, so this particular phenomena is called as transitivity in the networks. So more the number of common friends we have. So more the number of common friends Rishabh and Vibhas have, the probability of these both becoming friends increases. So now transitivity, it plays a very crucial role in the social networks. So how it plays an important role. So like first of all, I would like to mention that the transitivity, how to measure transitivity in the networks. So there is this measure called as clustering coefficient. So we will study this measure called as clustering coefficient. So clustering coefficient, it quantifies the transitivity in the network. Okay, so the higher the clustering coefficient, the higher will be the higher will be the possibility of your friends becoming friends with each other. Okay, so the higher will be the probability of friends becoming friends with each other, and higher will be the probability that this particular group is a closed group. By closed group, I mean that this is a strong group. I mean, like you might have seen like in the companies, like we sometimes we talk like this, okay, don't tell to this particular person because he is very closely connected to that group. Okay, so we generally say that in that sense that this particular person with whom like we are intending to share an information that closely knows the entire group, he is connected to all the other groups. Okay, so yeah, so this is transitivity. And like also like the high clustering coefficient, if a node has high clustering coefficient, so first of all the clustering coefficient is a vertex measure. Okay, so it is a measure for each and every vertex. So for each and every vertex we will be calculating this measure called as clustering measure, and it tells you what is the structure of the nodes around you. Okay, so now we can have these different structures. For example, here you see that a particular node, all its neighboring nodes are not connected to each other. In this particular case, the clustering coefficient is 0. But like on the other case, on the other hand, we have this particular node that is black in color. All its neighbor are interconnected to each other. So in that case, the clustering coefficient is higher, that is 1. Okay, so yeah, so I would also like to add another interesting fact in social networks. So there is this research study done. So if there is a person, Okay, and does that person do not have any common friends between their friends? Okay, so for example, this person, okay, so this person has four friends, but those four friends are not friends with each other. So if this is a real world scenario where a person is friend to certain people and those people are not friends with each other, so in that case the probability of this particular person having depression increases. So there is this research study done in social media analytics on this particular type of networks. So if your clustering coefficient is low, if a clustering coefficient of a particular person is low, then the probability of him getting depressed increases. Okay, so yeah, so that's why like this particular measure, that is clustering coefficient, it plays a very crucial role when we are trying to analyze that how the network is around a particular node. Now, how do we calculate this clustering coefficient? So clustering coefficient is actual connections among the neighbors to the total possible connection between the neighbors. Okay, so what we will be doing, we will be, for each particular node, I will try to identify that how many neighbors it has. Okay, so now for each of those neighbors, I'll try to see that whether there are connections between those neighbors or not. So if like those will be the actual number of connection. Then suppose there were k neighbors, then total possible number of connection is k into k minus 1 by 2. Okay, so that we will put in the denominator. So like in the previous example, okay, in this particular case, how many neighbors does this particular node has? Anyone?
4.
Yes. So it has four nodes. Now we look at all these four nodes. So how many connections these four nodes have? How many connections to each other?
0.
Yes. So 0 will be divided by 4 into 4 minus 1 by 4 into 3 by 2. Okay. So that comes to 0. So that's why the clustering coefficient here is 0. So now if we see in this particular case, the actual number of connection between the neighbors, how many are the actual number of connection between the neighbors?
3.
Correct.
3.
So 3 we will divide by 4 into 3 divided by 2. Okay, so that will be the that will come to 0.5. Okay, so this is how we calculate the clustering coefficient of a particular node. So now why clustering coefficient is important? I have already highlighted this fact that why clustering coefficient is important. Firstly, it tells that how a node's neighbor, that whether node's neighbor knows each other or not. Okay, so what is the probability of their friends becoming friends? So whether they know each other or not. Then the high clustering coefficient tells us whether the local community is strong or not. Okay, and if we have the low clustering coefficient tells us that the neighbors, they do not know each other. Okay, so now see, we have already studied this, that clustering coefficient is a vertex centric metric, and we can calculate the clustering coefficient for the entire network. So how you will calculate the clustering coefficient of the entire network? You will take the average of all the clustering coefficient for each and every node. Okay, so what you will do, you will calculate the clustering coefficient for all the nodes and then you will find the average of this. So this become the clustering coefficient of the networks. So if you see that the clustering coefficient was used to study different type of networks. So here we saw that the clustering coefficient for these particular networks was low, but then we see that there is a slightly interesting pattern we can see here. So in co-authorship network, which is a social network, okay, so co-authorship network, I have already explained you what is co-authorship network. So co-authorship network is a social network. So in the social network, suppose I have two researchers, okay, and there are lot of common people with which these two researchers have collaborated. So now if like now the probability of these two researchers collaborating with each other increases. So there is a very high probability that the researchers will collaborate with each other. So similarly, there are another interesting networks like the actor network and so on. So we can see that all the social networks, they tend to have high probability of high clustering coefficient. Okay, so now after studying the clustering coefficient tells us that how the structure of node is around a particular node. Okay, so next we come to this very important node measure, that is centrality. Okay, so centrality, it tells you that how important a particular node is in the network. Okay, so how important, how prestigious, how prominent a particular node is in the network. So how do we quantify the centrality in the network? So centrality is very important whenever you are doing some task that is related to ranking. Okay, so there can be a number of different tasks in social networks where we have to rank the people. Okay, so you have to rank the people, and how do you rank the people? You generally rank the people based on their importance. So these are the different measures that are used to rank different people in the social networks. So the first very easy and very straightforward centrality measure is the degree centrality. So degree centrality, in the last class we have studied that degree is number of edges that are incident on a particular node. Okay, so degree centrality is calculated by this formula. So degree centrality is degree of a node divided by maximum degree in the network. So if a network has, for example, 5 node, so what will be the maximum degree a particular node can have in this network of 5 node? Anyone? So if I have a network of 5 nodes, what is the maximum degree that a particular node can have?
4.
Correct. So the maximum degree will be n minus 1, because like each node can be connected to all the other nodes. Okay. So yeah, so the maximum degree will be n minus 1. So this is the formula for calculating degree centrality. There are other ways in which we can normalize the degree. Since, although like this is the most commonly used formula, but then there are other ways in which we can normalize this degree. So one is we will identify the actual maximum degree in the network. So that maximum degree we will divide by each of the degree. Okay. The third way is to normalize by degree sum. So we will calculate the sum of all the degrees and we will divide the degree with this. So actually, like in the network, you need to normalize these degrees between the value of 0 to 1. Right. So why do you need to normalize these values? So because so for example, I want to compare two different networks. So now if I have these two networks, in one network, I might have the degrees. Suppose there are like 100 of nodes. So I might have degree ranging from 1 to, for example, 20. And there is another network which is of smaller size, and then they have degree maybe like 1 to 10. Now I want to compare these two degrees. So I cannot directly compare the degrees of these nodes because there is difference in sizes of these networks. There might be difference in the density and so on. So I cannot directly compare the degrees of these two networks. So in these cases, we need to normalize the degree. So that is why the degree centrality is always a normalized version. So whatever the importance measures we are going to study, they are all normalized versions. So you cannot use the direct value. You always have to normalize those values. So yeah, so I want you to take this example and maybe you can calculate the degree centrality of node A. So quickly give me the answer by calculating the degree centrality of node A.
0.66.
Is this answer correct? Anybody else has calculated this answer? Yes, the answer is correct. Okay. So yeah. So now, like I might have the directions to these degrees. So do I have kept the example? Okay.
Ma'am, can you explain this, madam, in case of, this one.
This slide you want me to
Yes.
explain?
Yeah, just
Okay.
quickly you can. Yeah.
Okay, sure. So here we have all the nodes. So for each node, we have calculated the degree. For example, for A, we have degree 4. 1, 2, 3, 4. So 4 was the degree. Okay. Similarly, for B, the degree is 1, 2, 3. So degree is number of edges that are incident on a particular node. Okay. So once we calculate all those values, so how do we calculate degree centrality? Degree centrality is degree divided by maximum degree in the network. So since we want the normalized version, so here we have 1, 2, 3, 4, 5, 6, 7, 7 nodes. So the maximum degree in this network will be 6, that is 7 minus 1. So what we will do is we will divide 4 by 6. Okay, so you get the centralities. So this is how you will get the centralities for all the other nodes. So now when you get all the
Ma'am, you said maximum degree is 7, right, madam? How did we get that maximum degree?
no, maximum degree is 6. Why 6? Because like this network has 7 nodes. Okay, so for example, I have this node A. What can be the maximum degree of A? Maximum degree of A can be when A is connected to all the other nodes. How many
Yeah,
nodes are there? How many remaining nodes are there? There are 6. So what will be the maximum degree in this network? The maximum degree will be 6.
6. Yeah, yeah.
Yeah,
Oh,
yeah.
good. Thank you.
So once we have these degree centralities, we can order these nodes based on these values. Okay, so that is how you are getting the ranks. Now C has the highest rank, C has the highest degree centrality, and like so on for the other nodes.
Thank you, ma'am.
So,
Clear, ma'am.
yeah, okay. So now you might have the example where like there are directed edges. Okay, so in social networks, sometimes you have directed graph, sometimes you have undirected graph. So I'll keep the example of directed graph as well when I'll upload the slides. But currently, like I do not have the directed graph here, but I'll explain you here. So yeah. So you might have a graph that is directions and that has in degrees and out degrees. So I hope this particular term is clear to everyone that how do we calculate in degree and how do we calculate out degree. Okay, so the number of edges that will be incoming to a particular node that will be in degree and the number of edges that will be going out. Okay, so that will be the out degree. Okay, so we will calculate in degree and out degree separately. So once you calculate in degree and out degree separately, you can have separate degree centrality based on your in degree and out degree. So what you will do is you will divide out your out degree with the maximum degree in the network, or you will divide the in degree based on the divided by the maximum degree in the network. So I will put the slide and by seeing that example, it will be more clear to you. So yeah. Now this was the degree centrality. So what is the application of degree centrality? When do you want to rank the nodes based on degree centrality? So can anyone give me an example?
To find out, say, in social network, who is the most influential or important person?
Right. So yeah, so in the network, if I want to identify that who is the most popular person or who is the celebrity. Okay, so generally, like, there will be a lot of connections in the social network to the celebrity, and the celebrities will have exceptionally high degree centrality. So yeah, so whenever you want to identify, you want to rank the nodes based on their influence, okay, or you want to see that which one is more popular, which one is less popular. So in those cases, we use this measure called as degree centrality. Okay, so now there is this next measure, that is closeness centrality. So now, what is closeness centrality? In closeness centrality, we try to identify which node is close to all the other nodes in the network. Okay, so what do you want to identify? You want to identify which particular node is close to all the other nodes in the network. So suppose there is some information that I want to spread really quickly. Okay, so I will try to identify the person who has high closeness centrality, and I will give that information to that person, so that person will quickly diffuse this information in the network. Why? Because that particular node is closer to all the other nodes in the network. Okay, so yeah, so this particular centrality measure, we try to identify the nodes based on this centrality measure whenever this particular thing is important to us, that how fast our information is spreading in the network. Okay, so now how do you calculate closeness centrality? You calculate the, for example, you want to calculate the closeness centrality of a node V. Okay, so what you will do is you will calculate the shortest distance from V to all the other nodes. Okay, so you will calculate the shortest distance from V to all the other nodes, and then you will divide by the you will divide by the actually you'll the closeness centrality is inverse of the shortest distance to all the other nodes. So the inverse average, sorry, I'll rephrase it again. Closeness centrality is inverse average of the shortest distance to all the other nodes. Okay, so this is the case where, like, we need to apply the algorithms like Dijkstra algorithm. Okay, so you see, you will start appreciating that why we have covered those algorithms previously. Okay, so at the backend, so now you will be using network X to implement this closeness centrality. But actually at the backend, how the closeness centrality works, it uses one of these algorithms, right? The Dijkstra algorithm, in order to find the shortest distance to all the other nodes. Okay, so what all are the applications? Identify, okay, how effectively the information spreads in the network. Okay, so yeah, so then like also when we need to track the disease spread. Okay, so suppose a disease is spreading in the network, so I would want these people who have like high closeness centrality to be vaccinated first. So you might have seen when the COVID vaccine started. So initially they identified the people, like they identified that all the people who are working in government sections, they should be vaccinated first. Okay, so why they identified those people? Because those people who are working in public domain, they are meeting a lot of people, right? So they are generally, they have high closeness centrality, so they are meeting, they have lots of connection, and they meet a lot of people. So we need to vaccine these people first in order to avoid the spread of disease. So yeah, so now let us suppose we have this particular network. So I want you to calculate the closeness centrality for node A. Okay, so in order to calculate the closeness centrality for node A, you need to identify what is the length of shortest path from A to B, A to C, A to D, and A to E. Okay, so once you calculate all that, you will divide it by 4. That is n minus 1, and is the total number of nodes we have here. So that will be the inverse average. So please calculate it and give me the answer.
That's 0.67.
Yes, the answer is correct. So here, like I will share this slide. You can follow this solution and you will get the closeness centrality. Now I have one question for you. Why we are using this inverse distance here? So why are we using inverse shortest summation of inverse shortest distance? Anyone?
Because the influence is inversely proportional to how far the person is.
Right.
Influence.
Right. So I can rephrase it for you all. So suppose so suppose the average distance from me to all the other people in the network is huge. Okay, so suppose like I am quite far to all the other people in the network. So if I'm quite far, then the average distance value will be higher. Okay, so average distance from me to all the other nodes will be higher. Okay, so this if the distance is higher, I want the centrality value, the closeness centrality, my closeness centrality should be low. Okay, so that's why there is inverse proportional relationship between the average distance and the closeness centrality value. So if the average distance is more, I want the centrality value to be if the average distance is more, I want the closeness centrality to be less. And if the average distance is less, that means like I am very close to all the other nodes, then the centrality, closeness centrality should be high. So there is this inverse relationship. That's why we are taking the inverse relationship here. Okay. So now this is not the only, these are not the only two centrality measures in order to identify that which are more important nodes, which are other important nodes. So there is another notion of betweenness centrality. Okay, so now you can see that I have these two groups, C1 and C2, and there's a node in between these two groups, that is V. So whenever I have this application that suppose I want I want to pass some information from group C1 to C1, C2. Okay, or in the other words, I can say that okay, if I have to book some property, okay, if I have to book some property, I have to go through this particular person only. Okay, so in that case, this particular node has a very high centrality measure. So this particular node, the node that has high betweenness centrality, that sits between two groups. And now this particular node that is sitting between two groups, that becomes very important when we need to communicate from this group to that group. Okay, so that's why in this particular case, the centrality or the importance of this particular node who is sitting in between these two groups becomes more. So it might have less degree. This point should be like noted that this particular node who is sitting between these two groups might have a low degree. It has just 2 degree, but whereas if you see V1, V1 has high degree, that is 5. Okay, but the importance of this node is more in terms of when it comes to passing the information from one particular group to another. Okay, so the application of this is again like in epidemiology, when we are trying to vaccine the people, I would try to identify those people such that okay, agar yahan pe COVID hai, to it should not pass to this group. So how it will not pass if I vaccine this particular person? So you have to identify those people who can stop that propagation. okay, who sits between the group, and like if all the information, or if everything is passing from this node to another group, then this node becomes very important, and that is the betweenness centrality. Okay, so now this epidemiology was one of the application. Then there can be another application. For example, there is this highway. Okay, so there is this highway that is connecting two states, maybe Telangana and Karnataka. Okay, so now this is the only road that is connecting these two cities. So what I would like is that this particular road should not get blocked. Okay, so the maximum resource should be allocated when this road is being built, because this is a very important road when connecting these two states, and this has the probability of having high traffic. Okay, so yeah, so when building these roads, or when building the pipeline network, we need to identify those pipes or those roads that has high betweenness centrality. Okay, so yeah, so you can see that all these different centrality measures, they have different notions. Okay, they have different meaning, they have different semantics related to it. In different situations, we need to use these different centrality measures, and based on the application, we can decide which centrality measure you want to use. Okay, so another intuition. Okay, so what do you think that how we will calculate the betweenness centrality? So I would like you to spend some time on this and try to figure out how you will calculate the betweenness centrality of a particular node. So this is, I will give you one hint. This is something related to shortest paths again.
Is this a homework or we have to do it now?
No, now only.
Yeah.
Just try to think that what could be the formula for betweenness centrality. It is something related to shortest paths. Anyone
Yes,
want to try?
I guess the distance from V to V1 and V2.
Okay, so yeah, so I'll give you the answer. So this is in this particular case, like when we are trying to identify what is the betweenness centrality. So we will try to calculate the total number of shortest paths that pass through this particular node. Okay, so total number of shortest path between any pair of nodes. So total number of shortest path that pass through this particular node divided by the total number of shortest path in the entire network. That will give you the formula for betweenness centrality. So yeah, so suppose S and T are any nodes in the network, and we are trying to calculate the betweenness centrality of node V. Okay, so now these three are the nodes. Now what we will do, we will try to identify the shortest number of shortest path, total number of shortest path between any two nodes that are passing through V, divided by all the shortest paths in the network. So this is the formula for betweenness centrality, more the number of shortest paths that are passing through this node. So you see that like there are many shortest paths from this group to this group. Okay, so more the number of shortest path that will pass through the node V, more will be the betweenness centrality of that node. So yeah, what are the application? The application is that it helps you to identify the bottlenecks and the key influencers. So it identify those people who are important for connecting two different groups. And for example, in like a road network, so if you remove the resources to this particular road that has high betweenness centrality, it can disrupt the communication between the networks. So yeah, this is one of the example that you can work out. Here we are not calculating the betweenness centrality, but we are calculating the total number of shortest paths that are passing through B. Okay, so when we are trying to identify the number of shortest path that pass through B, okay, so first we need to see that, okay, from A to D, what is the shortest path? The shortest path is ABD. So in this particular shortest path, B is there. Okay, so this is like one of the shortest path has B. Now, what all are the other from A to C? B is not there. From A to E, again B is not there. Okay, now from C we try to identify. From C to A, B is not there. From C to D, C to D, this is one of the shortest path, and on this path B resides. So we have number of shortest path that passes through B, now 2. Okay, and then C to E, there is no
One
like
question, ma'am.
yes.
So when you say C to D, we can even come from C, E, and ED, right, ma'am? That doesn't have a B in it.
Yeah, yeah. But then one of the shortest path passes through B, right?
Yeah, yeah.
So
Okay.
yes, yes. Again, from B, from E and from D, we will be calculating. So this is how we calculate the total number of shortest paths that pass through a particular node, and then we divide it by the total number of shortest paths in the entire network. So that gives you the betweenness centrality. So yeah, with that we end today's portion. So in the next class, we will be discussing a very important algorithm, that is PageRank algorithm. And before that, we will be discussing eigencentrality. So eigencentrality is one of the centrality measure that try to quantify those people who are connected to important people. So the notion of importance here in the eigencentrality is that, for example, like I have one minister. So minister, definitely he is very important because like he has lot of connection, so he will have high degree. But then the PA of a minister, okay, the PA of minister is also a very important person. So the PA will also have high centrality. Why? Because it is connected to an important person. Okay, so when you try to quantify the importance of a particular nodes by whom they are connected to. Okay, so when you are trying to quantify the importance of a particular node by like whom they are connected to, whether they are connecting to some normal people or they are connected to some celebrities, so that particular importance is called as eigencentrality, and we will see the mathematical formulas in the next class. So up till now, any doubt, anyone?
In which book can we read more about all this? Or just find a book for topic by topic?
So, yeah, I can suggest you the book. Let me try to identify. I'll suggest you the book in next class. So there
Thank
are books like in which like these topics are very well written. I can suggest you the book in next class. I'll try to identify and post the link to the book. So yeah, with that, we will end the class. Thank you, everyone. Enjoy your weekend. Bye-bye.
Can we also get the PPT for both the
Yes, yes, I'll
sessions?
upload. I'll
Thank you.
upload it now only, just
Thank you.
after the class. Yeah.
Yeah.
Thank you.
Thank you.